Good morning. I see we have 86 people already registered, which is absolutely great. So I just want to welcome everybody. 89 now. It's absolutely wonderful to see so many people coming in. Have over 200 registered. Let's see how many join the webinar. So we have the second in this series, and this is very pleased, or we're all very pleased. Kate, Max, and Stefan and I that are running these, all very pleased about the take up and the offers to give webinars. And I think you'll know there's a lot coming up in future. So today you're going to hear from me on MT acquisition, from survey design to field procedures. And then next week we have a special webinar from Patricia de Legao, who is the 2020 SEG Honorary Lecturer for Latin America. And she's going to give us her webinar on environmental friendly exploration using magnetotellurics. And then the week after that is Max Moorkamp, who will be speaking on distinguishing molten fluids from graphite in the lower crust with multi-physics inversion. And the week after that, we have Karen Whitemeyer on autonomous underwater vehicle-based electric and magnetic field measurements applied to geophysical surveying and subsea structure inspection. So please go on to the webinar page, and here you'll see webinars for each week. Now we've gone weekly because there's so much interest. And then your Martins is already available as a video link. And then the upcoming webinars, you'll see registration links. And we have a number of excellent webinars coming up almost every week. Xavi Garcia starting off processing and analysis, and Ken Witherley. I've got his title this morning. I can put it in. But you'll see there's a very exciting plan for the next year. Just a couple of questions for those of you maybe not so familiar with Zoom webinars rather than Zoom meetings. In a Zoom webinar, you've got less webinar controls. You have your audio settings where you can set where your sound comes out. You have a chat function where you can send messages to all people or everybody in the all the participants. You have a raise hand function, and you press that, and then the hosts, and the host today is myself and Kate down in Adelaide and Max in Munich. The hosts will know that you want to speak, and then so that presumably will come towards the end when we have questions. And then we have a Q&A button, and you can send questions, and these are for the presenter to answer. Now, I'll try to answer those on the fly. I've got the screen open, so I can see there's no open questions right now. So as questions come up, I'll glance at them and try to answer them on the fly. But I may not succeed in answering all of them. Okay. So the takeaway message. The takeaway message, the one I want you all to walk away from, if nothing else, is to have the concept that it all begins in the field. Whatever you do in the field, you're going to take with you back to the lab, to the office, and you're going to process these time series, and you're going to try and analyze them, and you're going to try and invert them. And if you don't do a good job in the field, it's going to follow you through all of that. There's a lot of law about best practice in the field, and there's some fables. People have some weird ideas. But the common truth of all of this law and all of these fables is that if you collect poor data, you're going to be fighting to improve it in the lab through processing, and then you're going to suffer the consequences during analyses and inversion. And you're going to end up with a model with poorer resolution. So the objective of the survey, which is to give you a model of the Earth, is not going to be met as well as if you had good data. And my experience from seeing how people work is that perversely, people I've seen it in my students, postdocs, other people, colleagues, perversely people seem to be happy to spend 10 times as much time in the lab trying to correct the poor data that they collected in the field than they would have spent if they'd have spent a bit more time in the field. And I must admit, I've seen data collected particularly poorly by academics, maybe because a lot of academics are just come into the game and then leave the game, maybe because they've not been trained properly. And I would say that generally, the major MT contractors do consistently a better job, and this is because that is their job. Whereas a lot of academics, particularly students, they want to dash out, grab the data, and then dash back to the lab. So I want you to try and pause and think about that. So the first aspect you must do is survey design, and the overarching question is, why are you doing the survey? Just what is this about? So before you go into the field, spend time thinking about why you're doing the survey. And the answer to that question defines the instruments you'll use and station spacing and the frequency of interest. And recording time of day, etc. So there's some theoretical aspects I'm going to present now, and many of these you can control, obviously, but there's some practical aspects, and those can be more difficult to control. So the theoretical aspects, from an academic's perspective, again, what is the overarching question you're trying to address? And this you've usually articulated in your proposal for funding, so you know what that is. From an exploration perspective, the questions might be somewhat different. Do you wish to detect or delineate? If you're looking to detect anomalies, then really from a cost benefit basis, you want to use as few stations as necessary so you can get the greatest coverage you can. If you want to delineate, you want to put in as many stations as you can afford. And then the question is, do you need all 5 components at all stations? Perhaps you don't. And we'll explore that through a couple of examples. If you're going into a brownfields area, and for those not familiar with the term, brownfields means an area where there's been current exploration and there's been some mining activity already, then you'd know a lot about the likely conductivity structures. If you're going into a greenfields area where there's been no work done before, you know what type of structures you want to find. You know essentially what size of deposit makes sense, makes economic sense. You know the deposit target and the rocks, and you know the host rock. So you can generally build a model. So survey design, the theoretical part of survey design in MT is an awful lot easier than control source EM. You don't have to worry about or think about the source, unless of course you're in the auroral or equatorial regions. So what you're trying to do is 3 things really when you do survey design. You want to know the frequency range of measurements that you need to acquire to optimally image your target. You need to know what your target is. Is it crust mantle boundary? Is it a lithosphere, asthenosphere boundary? Is it a geothermal deposit down at 2 kilometers? Is it a mineral deposit down at 1 kilometer? You need to know what the frequency range of measurements is. And are the AMT data or MT deadband data crucially important for detection and resolution? And what's the lowest frequency or the shortest period that you need, and that defines the time of acquisition. Station spacing, you can do wide spacing for detection and tight spacing for delineation. But then types of measurements to make, do you need all 5, or is it sufficient to make only inline E fields, this so-called EMAP, or MIMDAS on Titan 24 examples, where you're not measuring the magnetic component at every site, maybe not measuring all electric components at every site. So I'll just show you a survey design that I did and presented 18 years ago now, when I was with the Geological Survey, and my colleague, former student Gary McNeice, was with a company called Geosystem. And we presented this at the SCG, and we wanted people to think a little bit about the nature of how fields act as they penetrate into the ground, particularly for steeply dipping mineral targets. And so the objective is to understand the response of a typical Canadian ore body in terms of its EM fields rather than its responses, leading to efficient and effective survey design. So the body we took was from Kidd Creek, or Kidd Mine, and this is one of the world's largest BMS deposits. It's copper, zinc, and some silver, and it actually has the credit right now of being the deepest accessible non-marine point on Earth. Those of you in South Africa, if there's anyone listening, you'll complain, wait a minute, we have deeper mines in South Africa, but you start at 1,500 meters height. And so you don't go as deep in the Earth as this mine does. It goes down to 2,700 meters below sea level. And so this was the extent of knowledge in 2002, and I took this image from Falcon Bridge's website. Falcon Bridge was a mining company that got taken over by Xstrata in 2006, and Xstrata itself was taken over by Glencore 2013. So this deposit is owned by Glencore. And what they knew at that time was this was the mined out ore in that light brown color. And they knew that there was ore down to 3 kilometers that they called Mine D, that they were just about to start mining. And so the question I had is, could we observe this ore from the surface? And so I used a very simple model of the ore. I knew something about the resistivity of the ore and the resistivity of the host rock because of studies done by John Katsubi, Geological Survey Canada, who's done rock property measurements on the ore from this body. And I knew it was on average about 10 ohm meters. And so we could characterize this body by this simple structure. Okay, so here's the simple structure down at 1.4 kilometers, going down to 3.1, with a width of about 100 meters and a dip of 83 degrees. And we're doing this in 2D because it had quite a long 800 meters, 1 kilometer length extent. Host is very resistive, 10,000, and very tight site spacing because I wanted to see optimally what's the very best we could do. So here's a very simple model of a dipping ore body of 10 ohm meters in 10,000 ohm meters. What's the response of that ore body? And I'm going to show these in terms of phases because, of course, in MT you could have static shift effects. So here's the anomalous phase. What that means is I've taken the TE phase and subtracted 45 degrees, which will be the half space. So here you can see the anomalous phase, and you can see clearly as you're going across the body. So here's a 7-8 kilometer line. You can see 2 phase highs or 2 phase maxima and minima. Phase maximum or minimum, depends which way, whether you subtract 45 or subtract the anomalous from 45, of minus 22 degrees at 100 hertz, centered on 100 hertz. And then another anomaly at plus 22 degrees, centered on 6 hertz. That's the TE. Let's have a look what you have in TM. The range here has changed dramatically now. It's sub 1 degree. So this is the anomaly that you get in the TM. So these are your electric fields along the profile, your magnetic fields along strike, and of course the magnetic field is uniform because it's TM mode. So you're looking at the electric field variation on the surface. Very, very weak asymmetric TM response. A half a degree anomaly at most at 600 hertz, 0.2 degree anomaly at 150 hertz. What this tells us immediately is that electric fields along the profile are insensitive to this body. So let's have a look now at the vertical fields. And this is the amplitude of the vertical field response, the amplitude of the tipper response. And you can see that it shows of course, a crossover over the middle. Tipper's very, very sensitive to the vertical location, and a very strong anomaly of 0.27 on either side at about 2.5 kilometers from the body. So you're seeing this body already 2.5 kilometers away, and the decay is quite slow. It's a slower decay in tipper than it is in TE. This is much faster decay. Look, about 5 kilometers away, you've got almost no response. Whereas in tipper, you've still got a very strong response. So the vertical field is much more sensitive to this body in lateral distance. So in terms of fields though, here's our telluric amplitude spectrum and magnetic amplitude spectrum for a site right on top of the anomaly. And the black is the half space. So it's uniform because it's a half space, a uniform magnetic field in black. And there's the electric field you'd get in the half space. And then when you put an anomaly in, look what happens. Of course, you get a decrease in the electric field because you've got a conducting structure. And that decrease is about 28% at 33 hertz. The magnetic field, however, has got a 74% an increase at 12 hertz. And so the thing that astounded me when I did these calculations, I just hadn't expected it, but there's most of the anomalous response in MT at the sites above this anomaly are due to the anomalous magnetic field, not the anomalous electric field. So let's just put some overburden on top of this now, 30 meters of 25 ohm meters. How will that affect our response? Well, of course, it attenuates the high frequencies, and that high frequency anomaly that we saw before, it's all been attenuated because of the sediments, and now the maximum in the TE has been pushed down to about 30 hertz and has been reduced from 22 degrees to 15 degrees, and the maximum, the second maximum has been pushed down to about 3 hertz. In a TM mode, our maximum anomaly now is below 0.1, so there's no way we could ever see this anomaly in TM. The vertical field is the same response. We're getting attenuation of the high frequencies, and we have a maximum anomaly now of about 0.15 hertz at 9 hertz, but it's still got a very slow decay. You can still see it 5 kilometers away above noise. So these are the spectra now, the telluric and magnetic amplitude spectra. And this is what we had before. And these are the new spectra in dashed lines. And you can see what's happened is that the anomalous response has been pushed to lower frequencies. And in fact, the maximum anomalous response in the magnetic field is now at 6 hertz. And this is really important because it's been pushed into the MT deadband. So here we have an anomaly that we want to image that's fairly shallow, 1 to 3 kilometers, but its maximum anomalous response, because it's got overburden, is in the MT deadband. So steeply dipping, electrically thin, mineralized targets pose a problem for AMT detection and delineation. We have no measurable TM response. We got strong TE and transfer function responses. Most of the anomalous response is in the magnetic field rather than the electric field. we have greater lateral detection sensitivity in our tipper functions, but at lower frequencies. And what this drives us to do is say, look, we need to make measurements for this type of anomaly. We need to make measurements of all 5 components at every site. And we need to conduct, that emphasizes the point about conducting survey design. So a different anomaly that we looked at was presented at the same conference actually, was by Pilar Queralt and Juanjo Lado and I, when Pilar spent some months at the Geological Survey. And here we really did as good a job as we could on a realistic body. And this one was in the Bathurst camp in New Brunswick. So we published this paper in 2007, and you can read more details there. So our thinking was we wanted to construct as realistic as we could a 3D anomaly and look at the AMT responses in terms of design of a survey to detect and delineate conductive ore bodies. And so here's Canada, which lies above the United States. We won't talk about the United States today. Here's New Brunswick in red. And here's the province of New Brunswick, and the Bathurst camp is up here, the Bathurst mining camp. And we're going to look at the biggest deposit in that mining camp, which is deposit number 12, but it's labeled as 8 here for some reason. And we know an awful lot about this deposit because the Geological Survey and the provincial agencies and the mining company involved did an awful lot of mapping and drilling and logging and all sorts of stuff. So we know it really well. And here is a surface exposure of the structure. And we're going to be looking for these massive sulfides that contain 6% lead zinc. So on this undulating feature here. And we're going to image along a profile A prime. And in section view, you can see that it's, again, a steeply dipping target. It doesn't have the length extent that the Kidd Creek mine does. So here is one version of our anomaly. We did a number of them, some more complicated, but this was the simplistic in terms of resistivity. It had the geometry of the ore body, but it simplified the resistivities. The resistivities were much more complex. But for the sake of this analysis, for this particular study, we looked at a uniform host of 1,000 and a conducting body of 2 meters. And it's down, you can see the length extent, 1,300 meters, a width of 250 meters, and it goes down to 1,375 meters. And here's a profile going right over the top of the middle of this. And we have obviously the quasi-TE mode along strike and the quasi-TM mode. So we did this modeling using Randy Mackey's code of the day. We did it on a Sun Ultra, and this was, you got to remember, this is 18 years ago. It took us 2 days of computations to get the forward solution at 11 frequencies. And we generated synthetic data and we added noise and scatter. So these are the apparent resistivities now. Here's the diagonals and the off diagonals, and we've sliced through these to show where the features are. And you can see it's a very 3D response. If we slice through this and look at it in terms of 2D, here you can see the TM and the TE responses, so quite strong. And in terms of phases, maximum phase response at 100 Hertz. I won't go into any more details on this because we published the paper and don't have a lot of time, but just to conclude that what this very complex 3D body showed us, we analyzed it in 2D and in TD. We had very strong TE and transfer function responses. Whoops. Sorry, that was a wrong slide. We need the whole frequency range of AMT to detect and delineate the geometry of the 3D body. if you try to do 2D inversion, you can take all of the quasi-TM data, but only the high frequency TE data. The quasi-TE data behaves very 3D and is very different from the 2D equivalent and is highly sensitive to the length of the strike of the body. For this 3D body, different from Kidd Creek, most of the anomalous response is in the electric field, and the horizontal magnetic fields are small compared to the 2D version. So to optimize data acquisition, you could think about having stationary magnetic sensors and multiple electric field measurements. So in terms of practical aspects of your survey design, what magnetometers are best for imaging your target? What electrode should you use? Do you need to record in the AMT deadband, or do you need to record in the MT deadband? Or do you need to record very low frequencies? What will the cultural noise likely be like, and where should the remote be sited? These are all very important considerations as you're designing your survey. In terms of magnetometers, the answer depends on the frequencies that are best for imaging your target. Coils are excellent at high frequencies above 1 millihertz or 1,000 seconds. Squids are not in common use in MT. They're in much more use in, for example, airborne EM. We did use them in mid-80s, but they fell out of favor. It's just difficult to get the cooling fluid into the field. Ring core flux gates perform far better at the longer periods. So mostly we're looking at coils, and in coils it's a trade-off, and the trade-off is between lots of turns over a magnetic permeable core, which gives you much greater sensitivity, especially at low frequencies, but it gives you larger eddy currents in the core, so you get high frequency noise. So the opposite is a smaller coil, so smaller core with fewer coils. This gives you lower sensitivity at low frequencies and lower eddy currents in the core, so lower noise. And I'll show you as I picked the Phoenix family because they show this particularly nice graph. The Phoenix has this conventional coil family, an AMT coil called AMTC30, and then a couple of broadband coils called 50 is the big one, and 80 is the more portable one. And here on the left, you can see the responses of those. So I've highlighted the AMT deadband and the MT deadband. And these are the ranges you might be interested in. If you're doing mineral exploration, you're generally looking from 10 Hertz to about 10 kilohertz. If you're doing hydrocarbon exploration, you're generally looking from 10 Hertz or maybe 100 Hertz down to about 1,000 seconds. And if you're doing lithospheric exploration, you're generally looking from about 1 second to 10 to the 4 and higher. So just looking at these three, knowing where your target is, if you only had to choose between those coils, you would say, well, if I've got a mineral target, I'm going to pick this AMTC30. If I've got a hydrocarbon target or a deeper target, I'm going to pick this MTC50. You might choose the 80 if you're going in a helicopter, for example, because it's a smaller, more portable coil. So there's lots of these, and here's just a couple I've taken from the literature. One comparison produced by Dennis Woods of Discovery International that he presented at PDAC in 2013. He was primarily interested in the high frequencies, and he plotted it with frequency increasing, so the opposite way around. And he compared a number of manufacturers. And then Ian Ferguson, in his chapter, compared a number of coils. So you can see where you are. If you want to buy a coil, you can see which might be the best coils for the problem you're mostly interested in. There has been an attempt by a number of manufacturers, and again, I'm picking Phoenix because I know them well and their literature is available, including their specs. hybrid coil they call the MTC 150 and 180. The 180 is the portable version of the 150. And what they want to try and do with these 150s and 180s, which is the orange and the purple and blue, they want to try and have a coil that does it all, does both AMT and MT. As you can see in this comparison though, their hybrid coil isn't as good as their AMT coil at high frequencies and isn't as good as their low frequency coil at low frequencies, not surprising. It is superior in that overlap range. The biggest advantage of this single coil though is that you use one coil so you can do both AMT and broadband overnight. And so as long as you've got enough signal to be able to go through the AMT deadband, you're going to do very well with these hybrid coils. What electrodes should you use? Again, the answer depends on the frequencies that are best for imaging your target. Do you use metal plates or rods? Well, you can if you're only doing high frequencies. Do you use capacitive electrodes or antennas? You can, again, but you've got to use very high frequencies. You can use non-polarizing electrodes at all frequencies. I don't know why I said for low, at all frequencies. And then there's another type, which is these active electrodes if you've got very high contact resistance. And they're good to frequencies up to about 300 hertz. They don't work at higher frequencies than that. So metal plates, great advantage, of course, is low cost, low maintenance, quick to deploy. Disadvantage is you can have polarization charge noise even at high frequencies. These capacitive electrodes, they have a fabulous advantage that they're very quick to deploy. You just lay them down. The disadvantage is that there might be low signal to noise, possibly up to a kilohertz. So they do work well, but certainly above a kilohertz. And it depends on the signal, whether you get good information above about 300 hertz. The standard coils, standard electrodes most of us use are the non-polarizing ones. And these are good at all frequencies. I don't know why I said just for low frequencies. They're good at all frequencies. Very low noise for broadband LMT applications. Disadvantages, they're slow to deploy. You've got to dig a deep hole. They're expensive. They need maintenance between sites, and they need maintenance during acquisition. And one thing that Phoenix does is it numbers them, and this is really important because you need to know when electrodes start to go bad, and you need to identify which ones they are. And it's much easier to do this if you keep a track of exactly which electrodes go in exactly which holes. So in terms of the active electrodes, these were designed by John Stott for Phil Wanamaker to go into the Antarctic. And the problem they were trying to address was high frequency attenuation when you've got a very large contact resistance. And here's an example from work I did with Shane Evans and Jessica Spratt up on Baffin Island at one particular site. This should have been up at about 10,000 ohm meters, but we had this huge drop at high frequencies in apparent resistivity, and you saw the phases going to 0 and below 0. And this is caused by the contact resistance approaching the input impedance of the receiver. And this sets up an RC circuit and attenuates the high frequencies. And so to counter this, John Stott designed some preamplifiers, and Phil has used them very successfully now in the Antarctic, and they're very useful in resistive areas, glaciers, snow cover, exposed rock. Disadvantages, they're expensive, and you need logistically, it takes more time because you need to have a second cable with power to go to the electrode for the preamp, or you could have a battery out there preamp, but it's logistically it takes more time. So do you need to record the AMT deadband, 5 kilohertz to 800 hertz? It's important to know this before you go in the field, because what happens, here's a plot from the paper I published with Xavi Garcia down in 2002. Here's some time series the amplitude spectra at a kilohertz over 24 hours at a site near Sudbury in Canada. And you can see you had very high energy, but the moment the sun rose, which is about 6:30, what happens is you get solar ionization of the atmosphere. It increases atmospheric conductivity by 2 to 3 orders of magnitude, and that hugely attenuates the AMT fields from distant lightning sources, and particularly in the AMT deadband. So you do only need 10 minutes of data, but you need the right 10 minutes of data. And almost always daytime atmospheric attenuation will mean that you're just not getting any signal in the daytime. So you have to record overnight. So it's a bit awkward. You'd need 10 minutes of data, but you've got to record overnight. And it's, of course, logistically not feasible to work at night. So this means setting the site up for overnight just to get 10 minutes of data. So this is one of the advantages of those hybrid coils. If you're doing broadband data, do you need to record in the MT deadband or at the very low frequencies below 100 seconds or a millihertz? And then you've got to be cognizant of the sunspot number. How much activity are you likely to see? For broadband data at frequencies less than the Schumann resonance, you have to think about this. And this is a plot I picked off the web just a few days ago, which is Dave Hathaway's latest predictions of how cycle 25 will go. And we should have just reached the bottom of cycle 24, the end of cycle 24. It's been very quiet this year. So it's been an anomalous year for more reasons than one. And we should see rise now. By 2004, 2005, we should see the peak in solar activity. So if you can organize your survey timing, try and aim for high peak times in solar activity. So in terms of cultural noise, what will a likely cultural noise be like? You might have dirty power lines where your main harmonic, either 50 hertz or 60 hertz, is unstable and varies, and or you have broad side lobes. I know for some work I did with Chavi down in up in Yellowknife, their power supply came from a dam on a lake north of Yellowknife, and the frequency varied with load. And so it's 60 hertz, but sometimes it went down to 58, and sometimes it went up to 62. So deep notch filters didn't work, and we had to design some other filters to take out those power line noise. DC trains, absolute bugger. They really screwed us in South Africa. They really hurt in Switzerland. Sometimes when you're working near mines, for some reason they have a lot of power in the mines, is a third of the main power frequency. So you'll find mines operating at 16 2/3 hertz in South Africa that has a 50 hertz main supply. Wells often have pumping, electric pumping. Power lines are a problem if they carry DC noise generated by trains, for example. They can carry that noise tens to hundreds of kilometers away, but they can also have cathodic protection. Cow fences, analog cow fences like you find in Ireland, are terrible, much worse than digital cow fences. You can take those out with delay line filtering or things like that, or radar. So you avoid them or minimize them as much as you can. You filter out the 60 hertz as much as you can. You record off peak. You can request that the noise be turned off. You use remote reference at whatever distance is necessary. And the remote reference is hugely important when you've got a lot of noise. Well, I'll talk about that in a minute. And robust or other processing. In order to avoid natural noise, if you like, you bury the coils, you bury the E-lines, or hold them down close to the ground. You protect the animal cables from sprays. Monitor gear in high traffic areas. Stop recording during severe thunderstorms. And shift recording if you can to avoid storms, people, and animals. And then the remote. This is something that really doesn't get as much attention as it should. Where should the remote be sited? Well, quite clearly, the job of the remote is to give you a clean signal that correlates with the signal at your site and doesn't correlate with the noise at your site. And so you need the remote not to be seeing the same noise as your site is seeing. And so you have to use a remote that's at a position that it won't see the same noise generation. I did some tests some years ago, and what I found was that if I put the remote for AMT, high frequencies, a kilohertz or so, if I put the remote, we did it at 25 and 50 kilometers away, and I found the remote at 50 kilometers away was too far. Didn't get a signal correlation. If you're doing broadband work, of course, long period work, you can have remotes up to 1,000 kilometers away like we did in South Africa. If you might have correlating noise over long distance, think about using two remotes. There's no point collecting poor data. You might as well sacrifice two sites as your remotes and collect good data or be able to process good data at one site. So now in terms of MT acquisition, before I talk about this, I highly encourage you to read the chapter by Ian Ferguson in the book, the MT Method book. Absolutely fabulous chapter. Ian goes into the physics and the mathematics of a lot of the things that I'm going to be talking to you about now. And he talks about them in great detail, and I'm going to just skim these points. So MT, what we're doing, we're recording 5 channels. We need to put vertical field in a hole. Well, I'll talk about a loop in a minute. You really want, it's best statistically if your X and your Y are orthogonal, and that's because then they don't have cross-coupling, they're not seeing the same noise. Orientation doesn't usually matter, as X and Y can be in any direction. You can rotate the time series before you process. But actually, in terms of signal perspective, it's best if one of the axis is along the strike of the target conductor. Now, this sounds a bit odd. I mean, you're going into a survey to find out what's there. And so you don't know the strike of the conductor. But if you do know the strike of the conductor based on geology, then think about orienting your each station so that you're oriented with one of your axes along strike. So here's schematically an MT site, 4 electrodes, 3 magnetometers. We try to put the coils in different quadrants so that there's no cross, we put them as far away as we can from each other so there's no crosstalk. And then we wire these up. When you wire them up, try to make sure that your wires are crossing all of the wires at right angles so that you don't have any pickup. Here's an MT system, my MT system that I did my PhD work on from 1972. Home built as they were in those days, data recorded on paper that I had to hand digitize. Absolutely wonderful. This is Rosemary Hutton, who was my supervisor, my mentor in my early days. Modern systems are very different from that. Low weight, low power consumption, wide frequency range, wide dynamic range, internal recording schedule that can be downloaded, and the latest innovations are recorders in the field can be accessible through cell phone network. They can be interrogated, data can be uploaded, and so on. And so I'm just showing you some complete systems from different manufacturers. GPS synchronized. You can have multiple units, high reliability, fast, relatively fast setup, and operating from very low temperatures to very high temperatures, and often with lightning protection in them. So we talked about coils, and here's a bunch of coils from a load of different manufacturers. You install them, you dig a trench, and you dig a trench as deep as you can, and the point about this is to avoid wind noise. Try and avoid putting your coils near trees because trees couple wind noise to ground movement. You want them oriented as well as you can to within 1 or 2 degrees. Best to orient them parallel and perpendicular to your electric lines, whatever orientation they have. Should be as level as possible, of course. And try and bury the coil cable so that there's no flapping around in the wind. Vertical coil, of course, you have to bury that as deep as you can. Often you put a little cap on top of it. If you're on hard ground, then, whoops, then you could think about using a loop. Somebody sent me a question about what's my thought on coil tripods. And I must admit, I'm not in favor of them. We got tripods when we bought some Metronics AMT coils in 1989, and we did a number of tests with the tripods. We tried all sorts of shielding, and there was nothing we could do to stop wind coupling and ground motion coming into our signal. You just have to bury them. What might be feasible, and here's a coil designed by Jim McNay at down at the in Melbourne, Australia, and this coil now is called the Armit, and it's used by Abitibi Geophysics. And this for time domain EM, but this coil could be used for AMT. It has specs close to those of the Phoenix's AMT coil, and you can just see how easy these are. You throw them out, and then you can work out the orientation in the lab. For lower frequencies, of course, you need much longer coils, and you have to shield it from wind vibration. But I think this is something to think about in terms of quick installation. Think about going into. Then we have our electrodes with a cable. So again, you can use a solid metal electrodes, and as Ian discusses in his book, they can have a high contact resistance. You have the faradic contact resistance given by this equation, where this is the resistivity of the host, the length of the coil, and of the rod, and the diameter of the rod. So if you have a 50 centimeter rod of 1 centimeter diameter in 1,000 ohmmeters, you have an intrinsic contact resistance already of 1,000 ohmmeters, and there's nothing you can do about that. You can't reduce that. If you bury it in dry sand, 5,000 ohmmeters, then your faradic contact resistance is almost 6,000 ohmmeters. And then once you start getting poor contact, that's assuming you got perfect contact on the whole surface. If you got poor contact, then this will dramatically increase. So what we commonly use then is, of course, non-polarizing electrodes. And this is a schematic of a typical metal electrode in its salt in the earth. So there's 3 main types of these metal in its salt. And the reason we do this is so that polarization charges don't build up. Copper sulfite is the cheapest, but the highest noise of the 3. Lead chloride is the most common. It's the medium priced. The components are cheaper and medium noise. And by far the best in terms of noise, silver chloride. Because of its expense, it's used in marine applications. There's a wonderful paper, it's old now, but it's from 1980, but still wonderful paper worth reading by Petit and Dupas that compared a lot of different aspects about electrodes. And then Ian published in his chapter a comparison of the noise levels of different types. And you can see how quiet the seafloor silver chloride coil is compared to the lead chloride. So you bury this for stability. You need to stabilize it against temperature variation, and you need a low contact resistance. And you really want to get this contact resistance as low as you can. Best to get it below 1 kilo ohm. And this is important for long period recordings. and you want to put it in some sort of conducting slurry. So you push it, you make this mud slurry that you've put perhaps salt in, NaCl, common table salt, or bentonite type mud. But what are you doing here? You've got to think about what you're doing. You're setting up electrochemical boundaries. You've got an electrochemical boundary already between this metal and the electrolyte. And then you've got an electrochemical boundary between the electrolyte and this slurry. And then you've got an electrochemical boundary between the slurry and the surrounding rock. So any of these boundaries could potentially be a noise source. So you have to worry about all three of them. One approach that we've used, particularly in Botswana, is an approach that I call the Russian bucket. And I don't know, I don't know who told me about this approach, but I think it was a Russian. But the idea here is that you dig as deep a hole as you can, and you put a bucket in it, and then you put the electrode in upside down, and you fill the bucket full of this conducting slurry. Of course, that means that this will not drain away. So in very permeable, arid environments, if you're doing this sort of thing, you might find even after a day that this is completely dried out. But in a conducting slurry with the bucket, so your electrode essentially becomes this interface at the top here. How can an electrode go bad? Well, it goes bad when you get precipitation from the electrolyte of the salt on the electrode. And this happens either when it dries out or over time. And when this happens, then the electrode becomes noisy and because of these polarization charges. And it can act like a capacitor, and it can build up charge. And so the sign of this happening is if you have a large DC. So it's like a battery. If you have a large DC value from the electrode, you know the electrode needs to be taken apart, and the electrode itself, the electrode wire, has to be cleaned, and it all has to be redone. So when you put in your E line in, of course, you need to know its length. It needs to be as straight as possible. That avoids inductive effects in the vertical field, from the vertical field. You've got to, of course, measure it, and you've got to shoot it in. Of all the different wire you can use, the best wire is a coax cable. And a coax cable, you fasten it, you leave its shield open at the electrode end, and you attach the shield to the receiver ground at the receiver end. And what this does now, it forms a Faraday cage, which reduces induction pickup noise. So noise from movement in the wire. So here's our conventional X array. How do we wire this up? Quite simply, try not to have any of your wires crossing. One important thing to note is that what we actually measure is not north to south in these boxes. We measure south to ground, north to ground, east to ground, and west to ground. So your ground is hugely important. I won't tell you how many times I've seen people putting the worst electrode at the ground location, and that's a huge mistake. The other problem is that if you have a poor ground at your receiver, then your receiver might start to charge up, and when it discharges, you'll get noise in the box, which will give you noise in your signal. Somebody was asking about different array configurations. Well, this cross array is the most common that we use. There's the L array that in certain situations you might use depending on access, or there's a T array, and this T array is kind of what is done by a Titan 24 layout. In the L array, the advantage is you're only using 3 electrodes. The disadvantage is 1 electrode is doing triple duty. And so if you've got noise at this 1 electrode, you're going to get the same noise in both of these. So you're then going to get correlating EX, EY noise. And depending how you estimate your impedance, this could lead to bias. If you have a T configuration, then you have one noise doing double duty, and that can be a problem itself. So now we've got our electrode in the ground and we splice it to our cable, our electrode line. And you have to make sure that you do that both the electrode line and the electric line are very clean, and you cut the wire back if necessary. I've seen in early days, I've seen some people using connector plugs here. That's a huge mistake because they very quickly rust, and then you start to get noise from charges. So you make sure this splice is very clean, and then you wrap it with electrical tape. Here's a picture I took from the internet showing a layout. I believe this is, I got this from Karen Christopherson. It's in Chile, I think. What's wrong with that picture? Well, what's wrong with that picture is that the electric lines are not held down. You've got to hold them. You've got to preferentially bury them. If you can't bury them, hold them down every half meter so that they're not moving around in the wind. Particularly on a big open plane like this, there's going to be huge wind motion. So once you've set your electrode array up, then you've got 3 measurements to make. And I'm surprised that this isn't more common knowledge. I've spoken to a number of people, particularly in academia, who don't do this sort of thing, but I highly encourage you to make these 3 measurements. One is you measure the DC between electrode pairs, you measure the AC between electrode pairs, and you measure the contact resistance between electrode pairs. What you're doing with the DC is you're looking for the bad electrode. If you find that one particular pair, and you can do north to south, north to ground, so you can identify which electrode is giving you more than 20 or 30 millivolts, you take that out and replace it. So it's very important you do DC measurements. AC measurements, not as important now as it used to be. AC measurements is basically giving the level of AC noise, and this is because you don't want saturations. Although the modern 24 and 32-bit systems have got such a large range that you don't have to worry as much about AC noise. Contact resistance. This you have to, I've seen people measure these with one of the digital multimeters and hold the probes on the electrode line for quite a while. What you've got to remember is this is an active measurement. You're actually sending current through the ground. And so what you can do, if you're not careful, depending on your electrode, particularly if you've got a noisy electrode, you can be charging up that electrode, so you can be making it noisy. So if you've got a digital multimeter, you've got to do this very quickly. You've got to do it in reverse. So you measure it one way, you measure it the other way, and have a look at your resistance. Now I would say try and get below 1 kilo ohm for AMT and 10 kilo ohm for broadband. And if you can afford it, because they're more expensive, I highly recommend you get an analog multimeter because they use far lower current than digital multimeters. Power supply, well, that's obvious, 12-volt batteries. You can use solar cells. We've done this at, when we had long period systems. Receivers, now we all know what they do. You connect, they digitize, filter, digitize, and store in memory. And here's a number of receivers from different companies. Change the battery out every day, recharge overnight. Then the remote reference, these are coordinated by GPS now, much better than it used to be. 30 years ago, 20 years ago, you had to use a 2-kilometer, 3-kilometer cable in order to get accurate timing. It allows you to put the stations great distances apart. One thing that's you should remember though, is that normally you take the magnetic field as the reference, but for the AMT deadband, it's actually the magnetic field that's the problem. So you might like to think about using the electric field at the remote for remote referencing. GPS, you can have problems, so you have to sort those out. So in conclusions, MT data acquisition is not easy to do. It really isn't. Unfortunately, people think it is, and they go out and they throw things in the ground and they collect crap data. It requires at least the same diligence, care, and attention as subsequent processing, analyses, and inversions. You've got to consider absolutely everything. The electrodes, the electrode lines, the coil cables, receiver, GPS remotes. And do not rush fieldwork. It's far better to spend more time in the field than to spend 10 times that time in the lab trying to resuscitate poor data. So just to finish off, I'd like to acknowledge the people who've been with me and mentored me on my journey in magnetometers since '74, particularly those who showed me how to do high quality fieldwork. And Rosemary was the first, and when I joined the GSC, Ron Kurtz was absolutely meticulous. And then the EMS Lab experiment, John Booker, and then people in the industry, particularly George Elliott and Jerry Graham at Phoenix. They really showed me how to do good fieldwork. And so thank you very much, everybody. So you can throw in your questions now. Sanjay asks about fiber optic sensors applications to magnetotellurics. You know, Sanjay, that's something that, wow, that's come totally out of left field to me. And I haven't a clue how to answer that. Just certainly haven't thought about that at all. Fiber optic sensors.
Alan?
Yeah.
Maybe some comment, I think, where I understand where this comes from, because in the seismological community, they use now these DAS systems, that can record sort of virtual seismometers, like, you know, by the billions nearly, or like by the millions. But at least from that perspective, of course, they're using very different principles to us.
Exactly. Well, I know the LOFAR array in the Netherlands actually is, and also is being used for seismological purposes. You can look at movement of the fiber optics, right? But I don't see the same. I'd have to think a little bit more about that, Sanjay. Any other questions? Oh.
You've got one in the chat there, Alan.
Yeah, I'm looking at it. I'm trying to pronounce the lady's name. Or I'm not sure if it's, sorry, I'm trying to pronounce the person's name. We use coal mixture in the electrodes. Do you know any remote method to get data from the MT tool during the sounding? We use coal mixture into the electrodes. Do you know any remote method to get data from the MT tool during the sounding? Oh, do you mean during acquisition? Yeah, well, it used to be the case that the boxes record, you could get data out of the box as they're recorded, but the modern boxes not as much so. But now the latest boxes allow you to access the data in real time. So I don't know if that answers your question, but you can, like the latest box from Phoenix Geophysics does allow you to access the time series in real time, so you can see just what is happening, and then you can decide to change recording type from AMT to broadband, or you can turn it off or turn it back on again. A question from somebody anonymous: does MT and GDS have any difference in source fields other than measured fields? MT and GDS, well, they're just, the two sides of the same coin. GDS, geomagnetic depth sounding, what we would call just vertical field measurements, 3 components. These were huge. GDS arrays were huge in the 60s and 70s, pioneered by Ian Goff. And Ian actually did some work when he was working in Canada. He had to worry about the source fields, and so they published a number of papers where because they had a full array out, they really could look at the source structure. And so one difference is that with GDS, if you have a lot of sensors out, you can actually worry about source shape. Whereas in MT, generally we don't have as many systems out. And the one thing I should have mentioned, in fact, is that I think MT, we're undersampled. We really need to get tens and tens of systems out rather than 5 or 6. You know, we need to have large arrays recording, but this needs the equipment to become much cheaper. So in essence, it's exactly the same stuff, MT and GDS. It's exactly the same, except the GDS does have the advantage that it can deal with non-uniform source fields. It has the disadvantage that it's a magnetic field only method, so you have no absolute level control of where your anomalies are. MT has a disadvantage that you almost always have to assume a uniform source field, but the advantage that you've got precise depth control. So Feng Jian is asking, is it possible to use capacitive electrodes frequencies lower than 1 Hertz? No, certainly not. From the studies I've seen, both capacitive antennas and capacitive electrodes performed poorly below about 300 Hertz. Okay.
Alan, just from my side, a comment and a question.
Yeah.
I'll start with a comment. So maybe there's somebody in the audience who can say, sort of confirm this, but if I remember correctly from some of the manufacturers, they don't really measure sort of, when they measure the electric field, sort of individually to ground, yes, and then form the sort of add those up. The ground is important, but the measurement is actually done between those 2 electrodes. I think, so I think it still means that you have to worry about the ground, but I don't think it's quite as crucial as you said.
Yeah,
some discussions.
Yeah, it's a differential preamp that's on the front end. But the differential preamp is, of course, based on the ground, and so if you've got noise on the ground, that noise can leak in to the differential preamp.
Yeah.
One thing that the new LEMIs, and this is something I encouraged Koropanov to do, the LEMIs have got 4 electric field channels, and so that allows you to play games in terms of your electrode array. You could set it up just like I said, with a south to ground, north to ground, and so on, and so they are completely independent. Or you could set up parallel north south and east west, so you could have four lines. It's a lot more work logistically to do it that way, but the advantage of having 4 channels is that you have potential redundancy.
Yeah, and my question is, so what's your thought on sort of horizontal versus sloped installation in terms of then impact on sort of the inversion? So I have had discussions with quite experienced people that have expressed vastly different views on this. So
well, there's nothing you can do if you're on a hillside. You've got to lay out your electrode line up and down the hill, and then the question is, what do you do with that? Well, optimally, what we should be doing, of course, is our modeling code should be modeling what we measure. It doesn't. The modeling codes assume we have point E-field measurements, and that's not what we're measuring. We're measuring potentials at 100 meters apart. And so what the modeling code should do is calculate potentials and then compute the potential differences exactly the same way that they're measured. And that way you could, if you have a code that allows for a slope, like a finite element code, you can actually get the same precise comparison between your numerical configuration and your field configuration. Okay, I got a question from Makoya Didas. What's the distance required from the coastline to install the MT station? Well, that all depends on what your depth of interest is. Generally, I would say you want to be something like twice your depth of interest from the coastline. So if you're looking down to the crust mantle boundary and it's at 35 kilometers, then 70 kilometers away, your coastline effect is probably going to be minimal. But that doesn't really matter. I mean, you can have it a lot closer, and then you can model the effect of the coastline. It's more difficult, of course, if you've got a very tortuous coastline, but if you've got rather uniform coastline, then you can model the coast effect, and you can model it using the approach of John Booker instead of trying to have layers that go increasingly thick and having thousands and thousands of very thin layers to try and model the slope. You can actually model it by solid layers that have increasing conductance as you move away. The biggest problem, though, with modeling the coast effect is not the bathymetry, it's the sediments. Of course, we know the bathymetry, and so we can model the bathymetric effect very well, but often on continental shelves, you'll have very thick sedimentary sequences, and you can get a conductance of the sedimentary sequence that's equal to or greater than that of the overlying seawater. And so if you want to model the coast effect, if you want that to be properly modeled in your code, you've got to know what the sedimentary thickness is, and you've got to know what the sedimentary resistivity is. So people have done some quick and easy things modeling the coastline by putting in bathymetry, but that to me is not the whole answer. There's more to it than that for most coasts. Does topographic effects produce any significant effect in MT data? Yes, it does. There's a wonderful paper by George Jurassic, and it's well known in 2D and in 3D. George Jurassic published a paper a few years ago. And if you have a uniform Earth, right, and you've just got undulations of a uniform Earth, and then you sit on top of a hill, and you don't model it, you model it as a uniform half space, then what that will do is it gives you an underestimate in the TE case and an overestimate in the TM case. And I think I've got that the right way around. So let's say it's 100 meter uniform half space that has got topographic undulations in it, then you'll get 80 for your site on top of the hill in TE, and you'll get 120 for your site on top of the hill in TM. The problem is that doesn't make a lot of sense, because topography is there for a reason, and the reason is that some rocks are more resistive to weathering than others. And so when you have a topographic effect, you've got to also think about the valleys. And so when you model the mountain, you've got to remember to model a valley, because the valley is basically full of sediments, conducting sediments. And that's where you get the static shift effects, where you get a reduction in the electromagnetic field in valleys because of the conducting sediments below. And there was a paper published recently that proposed that in fact you had an increase in the electric field in the valley. Well, that paper ignored valley fill, and so it was it's not appropriate. Is the reason the batteries changed every day because you want to keep the battery voltage at a certain voltage? Solar panel battery setup. Yeah, what we've often used for charging our systems is what's called marine batteries. Now, if you look at the power loss of a typical car battery, it goes steadily down to below 11 volts and then steadily drops below that. And depending on your system might operate to say 11.5 or 11.25. And so on a car battery, it will stop working after a certain length of time. Now, marine batteries are designed to operate, have a discharge curve that's different. They stay as high as they can and then plummet very quickly. And so a marine battery will actually last you longer than a car battery at the same site. And also you can get marine batteries in much higher ampere hours, 120 ampere hours, but the bloody heavy beasts. But certainly if you're going to put a solar panel and a battery array, then you do have to worry about the noise. We did this in our Baffin Island work, but we put some noise suppression because you've got your solar panel, you're converting DC to AC, then AC to DC, and each of those could introduce noise that can be picked up by your MT system. So you have to have filters on your transformers. Okay, a question from Lima Williams. If we consider anisotropy, then should we think about creating a particular survey layout? Yeah, that's a very good question, actually. You know, as I said, when you're laying out your site, you want to preferentially lay it out parallel and perpendicular to the dominant strike direction of your structures. If you know that, and you can look at local geology or something to get that, or you've done a survey already. But if you've got anisotropy then, and if the anisotropy is at a different angle from the strike direction, yeah, I don't know. I think I would still stick with the parallel and perpendicular to dominant strike of the conducting anomalies, Williams Lima. Mohammed asks for how much can we decrease the electrode distance when acquiring data in the mountains? That depends entirely on signal to noise. We often use short electrode distances for AMT because electric fields are larger AMT ranges. So instead of 50-meter or 100-meter, if you like, electrode array, we might use a 50-meter electrode array, or we might even go down to sometimes a 30-meter, sort of 15-meter each line. But I've never done the test of how short you can go. I guess it's all a question of signal to noise. I mean, what we really would like, of course, is to have electrodes the size of those they use on the ocean bottom, which are just a meter, and you just plonk them down and you're done. But I don't think we can. Don't think we can do that on land. Okay, well, thanks everybody. We're at 20 minutes over time. I really really appreciate everyone coming to the webinar, and I hope to see you next week for Patricia's. It'll be an hour earlier, so 12 o'clock UT. And thanks everyone for attending. Bye.